Alright, we are back, and I've just been doing one upload a day, and I hope you guys are keeping up with it, because if you watch one of these videos a day, it's really not that much time, and it gives you some time to digest the information instead of binging them all at once. Do as I say, not as I do, because I did not do that in medical school, but hopefully this stuff is making sense. We're going to cover in this lecture these following topics, and the most important is definitely going to be the hemoglobin dissociation curve. Okay, so oxygen is transported in the blood. Should be no surprise to everybody as hemoglobin. Remember, there's hemoglobin F that you have in utero, and then I think when you're around 2 years old, that's completely gone. And then the majority of hemoglobin as an adult is, I believe, A1. There's also hemoglobin A2, but I think A1 is the most common. CO2 transport in blood is different. So, some people think oxyhemoglobin is the most common for oxygen. Carboxyhemoglobin is the most common transport mechanism for CO2. That is not true. It's like less than 5%, I think. The vast majority, around 90% or more of CO2 is transported in the blood via the form of bicarbonate. The way this happens is at the tissue, oxygen is delivered in the tissue, and then CO2 is returned back into the red blood cell. And then, do you guys remember this bicarbonate buffer equation? That is, the CO2 is converted via carbonic anhydrase to H2CO3, and then that's converted to hydrogen and bicarbonate ion. And then the way that the cell deals with the additional hydrogen ions, you don't want hydrogen ions building up because that's acidic, right? So it uses hemoglobin H to buffer it. Then at this point, the HCO3 does a exchange with chloride. That's what's known as chloride shift. And I remember there being a test question on that last year in one of the systems, or maybe the year before. Anyway, that's a fairly high yield concept. And this is, back to membrane biology. If you remove a negative ion, you want to replace it with a negative ion. So that's kind of how I think of it. Anyway, at this point, the HCO3 can kind of floats in the plasma, floats free, and then goes to the lungs. And then in the lungs, it's obviously converted back to CO2 before it's exhaled. Okay, this slide is muy importante. Might be a couple test questions from this slide. Some of you might already remember this from undergrad or know it already from your classes here, because it's a really popular concept, the hemoglobin dissociation curve. And you have to know, what's going to shift this to the right and what's going to shift this to the left. You just got to know it. And sorry about all those notifications. I don't know if you guys can see that or not. Dude, chill. Okay. So, some important concepts. What does a right shift actually mean? So that means there's decreased oxygen affinity for hemoglobin. And it also means that there's going to be increased oxygen offloading or unloading from the blood into the tissue. So again, we want a right shift at the tissues. Okay? But also, if you think about it, we want a left shift at the lungs. Some people remember L, left lungs, there's two L's. Because, we want the hemoglobin to hold on to the oxygen more tightly if we're at the lungs, right? Versus if we're at the tissues, we want the hemoglobin to release the oxygen more readily. And I don't know if you guys remember this concept of subunit cooperativity. And so there's 4 binding subunits on hemoglobin, and basically if one oxygen binds, it makes it more likely for more oxygens to bind, and that also makes it hold on tighter to the oxygen. And the reverse is true for the release of oxygen. That's an important concept, this cooperative binding concept. Another ways you'll see right shift in terminology can be called increased P50, and that's just right here. Oh, stop it. And I think it's just like where I don't know, increased P50. Yeah, okay. So you then like compare it over here on the y-axis. Increase. I don't know. Maybe it takes less. Increased P50 means it takes less something to saturate. Wait a second. I gotta figure this out, sorry. Okay, you look at it from the y-axis down to the x-axis. So to get to 50% hemoglobin saturation, it takes more PO2. I think that's what it means. What a right shift means. Yeah, that's it. Yeah, sorry, I had to figure that out. And then a right shifted hemoglobin is also in the taut form, or the T form. This is a mnemonic I found, and there's another one on the next slide you can use if you like it better. But it's like cadet face right. Found it on Google, and I kind of like it because increase in CO2 shifts it right. Increase in acidity shifts it right, and that means decrease pH or increase hydrogen ion concentration, right? The D is for DPG, 2,3-diphosphoglycerate. I've always used the term BPG. You can use either for bisphosphoglycerate. That shifts the curve to the right. E, exercise, is kind of famous for shifting the curve to the right. And then temperature. So increased CO2, increased acidity, increased DPG, increased exercise, increased temperature, all shift the curve to the right. And the reverse is true. If you were to decrease these things, they would shift the curve to the left. And this kind of sums it up. Hemoglobin affinity is highest where oxygen content is high to make sure of maximal loading. For instance, at the lungs, the left shift. And then hemoglobin affinity is lowest where CO2 content is lowest, like at the tissues. Dude, why does it keep doing that, man? Makes sure maximal unloading. So definitely understand this slide. Muy importante. I wonder why it was doing that. Okay. This is from first aid. This is just a further understanding, and it uses different mnemonics. If you like this mnemonic better, you can use it. Take a look at that. Okay, carbon monoxide poisoning is like a very high yield concept for boards. They love carbon monoxide poisoning, and it relates to that cooperativity, or cooperative binding concept again. Carbon monoxide actually binds hemoglobin at with 100% or 200% more efficiency than oxygen. So that's why it's really deadly. And actually, when you smoke cigarettes, you actually can give yourself some carbon monoxide poisoning. And then you get cyanotic because the hemoglobin can't deliver the oxygen to the tissues. So anyway, it binds to hemoglobin, displaces oxygen, and the hemoglobin molecule actually recognizes the carbon monoxide as oxygen. So then this is a bad thing in cooperative binding in this case, because if it recognizes it as oxygen, it's going to hold on to whatever oxygen is there more tightly, and that's a bad thing, obviously, right, in this case. So it technically causes a left shift of the curve. Left shift curve, carbon monoxide poisoning. The treatment for this, I believe, is 100% oxygen, because that's the only thing that can displace the carbon monoxide. This is kind of randomly thrown in here. I didn't know where to include it, but it's definitely good to know about chemoreceptors. So there are central chemoreceptors in the central nervous system, right, and that's in the medulla. And then there are peripheral chemoreceptors, and those are located in the carotid body and the aortic body. The central chemoreceptor, so both of these respond by increasing the breathing rate. And when we get to acid-base stuff, that'll make more sense. A decrease in pH and or an increase in PCO2, and these like go together, you know, like one kind of causes the other. For instance, in respiratory acidosis, if you are, like in the case of hypoventilation, or you say you overdose on benzodiazepines or opiates, you're not exhaling the CO2, then the CO2 is building up, and then you get respiratory acidosis, so there's a decrease in pH. So anyway, the response to those stimuli is increase in breathing rate. The peripheral chemoreceptors respond to the same thing, but also they can respond to a decrease in PO2 if it's less than 60 millimeters mercury. And this is good, right, in the peripheral nervous system, where the systemic circulation is, that it can sense a decrease in PO2 and tell our lungs to increase the breathing rate. And these, you know, the outputs of these nerves actually directly go to the diaphragm and the external intercostal muscles, which you know, ties back in those muscles of inspiration. You know, tells them to contract more tightly. Okay, which of the following situations we calls a right shift? And make sure when you come to the test day, you read the questions carefully. So right shift hemoglobin dissociation curve. Oh, I forgot to mention, you'll also see it called the Bohr effect. You don't see it as much, but you may see that term. Okay, fetal hemoglobin. No, that actually causes a left shift, and that makes sense, right? Because if a woman's pregnant, you want the hemoglobin that's delivering oxygen to the fetus to hold onto the oxygen more tightly than you would the hemoglobin that's in the adult. Does that make sense? Because you want to prioritize the fetus in a way. Exercise is the right answer here, causes a right shift, and that makes sense, right? You're increasing the lactic acid buildup, you're increasing the temperature, obviously, in your body, and your tissues need more oxygen when you're exercising. So you want maximal offloading of oxygen from the hemoglobin molecule. Increase in pH would cause a left shift, carbon monoxide poisoning, left shift. Now, I'm asking the opposite. What would cause a left shift in the curve? Decrease in DPG. That's got to be right, because an increase in 2,3-DPG would cause a right shift. Exercise, right shift. Increase in age, right shift, right shift. And we'll see later, but this molecule is super important in the response to high altitude. I forget how many days it takes to kick in, but chronic people that live, you know, for a long time at high altitude have a lot higher levels of 2,3-DPG, and that's why they eventually get a right shift hemoglobin curve. Hope I'm saying that right. But that's it for this lecture. Let me know if there are any audio issues. I've been trying to double check it and edit it if necessary, but I hope this worked.